An O-ring, also known as a packing, or a toric joint, is a mechanical gasket in the shape of a torus. It is a loop of elastomer with a round cross-section, designed to be seated in a groove and compressed during assembly between two or more parts, creating a seal at the interface. The O-ring may be used in static applications or in dynamic applications where there is relative motion between the parts and the O-ring. Dynamic examples include rotating pump shafts and hydraulic cylinder pistons. O-rings are one of the most common seals used in machine design because they are inexpensive, easy to make, reliable, and have simple mounting requirements. They can seal tens of megapascals of pressure. Manufacturing: O-rings can be produced by extrusion, injection molding, pressure molding or transfer molding. History: the first patent for the O-ring is dated May 12, 1896 as a Swedish patent. J. O. Lundberg, the inventor of the O-ring, received the patent. The U.S. patent for the O-ring was filed in 1937 by a then 72-year-old Danish-born machinist, Niels Christensen. He came to the USA in 1891 and soon after that patented an air brake system for streetcars. Despite his legal efforts, his intellectual property rights were passed from company to company until they ended up at Westinghouse. During World War II, the U.S. government commandeered the O-ring patent as a critical war-related item and gave the right to manufacture to other organizations. Christensen received a lump sum payment of $75,000 for his efforts. Litigation resulted in a $100,000 payment to his heirs in 1971, 19 years after his death. Theory and design: O-rings are available in various metric and inch standard sizes. Sizes are specified by the inside diameter and the cross-section diameter. In the U.S. the most common standard inch sizes are per SAES 568E specification. ISO 3601-1 2008 contains the most commonly used standard sizes, both inch and metric, worldwide. The UK also has standard sizes known as BS sizes, typically ranging from BS 001 to BS 932. Several other size specifications also exist. Typical applications: successful O-ring joint design requires a rigid mechanical mounting that applies a predictable deformation to the O-ring. This introduces a calculated mechanical stress at the O-ring contacting surfaces. As long as the pressure of the fluid being contained does not exceed the contact stress of the O-ring, leaking cannot occur. Fortunately, the pressure of the contained fluid transfers through the essentially incompressible O-ring material, and the contact stress rises with increasing pressure. For this reason, an O-ring can easily seal high pressure as long as it does not fail mechanically. The most common failure is extrusion through the mating parts. The seal is designed to have a point contact between the O-ring and sealing faces. This allows a high local stress, able to contain high pressure, without exceeding the yield stress of the O-ring body. The flexible nature of O-ring materials accommodates imperfections in the mounting parts. But it is still important to maintain good surface finish of those mating parts, especially at low temperatures where the seal rubber reaches its glass transition temperature and becomes increasingly crystalline. Surface finish is also especially important in dynamic applications. A surface finish that is too rough will abrade the surface of the O-ring, and a surface that is too smooth will not allow the seal to be adequately lubricated by a fluid film. Vacuum applications: in vacuum applications, the permeability of the material makes point contacts quite useless. Instead, higher mounting forces are used and the ring fills the whole groove. Also, round backup rings are used to save the ring from excessive deformation because the ring feels the ambient pressure and the partial pressure of gases only at the seal. Their gradients will be steep near the seal and shallow in the bulk, opposite to the gradient of the contact stress C, vacuum flange KF2FQF. High vacuum systems below 10 or 9 torr use copper or nickel O-rings. Also, vacuum systems that have to be immersed in liquid nitrogen use indium O-rings, because rubber becomes hard and brittle at low temperatures. High-temperature applications: in some high-temperature applications, O-rings may need to be mounted in a tangentially compressed state, to compensate for the gauge effect. Material: O-ring selection is based on chemical compatibility, Application temperature, sealing pressure, lubrication requirements, durometer, size and cost. Synthetic rubbers, thermosets, butadiene rubber, butyl rubber, chlorosulfonated polyethylene, epichlorohydrin rubber, ECH, ECO, ethylene propylene diene monomer, good resistance to hot water and steam, detergents, caustic potash solutions, sodium hydroxide solutions, silicone oils and greases, many polar solvents and many diluted acids and chemicals. Special formulations are excellent for use with glycol-based brake fluids. Unsuitable for use with mineral oil products, lubricants, oils, or fuels. Peroxide-cured compounds are suitable for higher temperatures. Ethylene propylene rubber, fluoroelastomer, noted for their very high resistance to heat and a wide variety of chemicals. Other key benefits include excellent resistance to aging and ozone, very low gas permeability and the fact that the materials are self-extinguishing. Standard FKM materials have excellent resistance to mineral oils and greases, aliphatic, aromatic and chlorinated hydrocarbons, fuels, non-flammable hydraulic fluids and many organic solvents and chemicals. Generally not resistant to hot water, steam, polar solvents, glycol-based brake fluids and low molecular weight organic acids. In addition to the standard FKM materials, a number of specialty materials with different monomer compositions and fluorine content are available that offer improved chemical or temperature resistance and/or better low-temperature performance. Nitrile rubber, a common material for O-rings because of its good mechanical properties, its resistance to lubricants and greases, and its relatively low cost. The physical and chemical resistance properties of NBR materials are determined by the acrylonitrile content of the base polymer. Low content ensures good flexibility at low temperatures, but offers limited resistance to oils and fuels. As the ACN content increases, the low temperature flexibility reduces and the resistance to oils and fuels improves. Physical and chemical resistance properties of NBR materials are also affected by the cure system of the polymer. Peroxide-cured materials have improved physical properties, chemical resistance and thermal properties, as compared to sulfur donor-cured materials. Standard grades of NBR are typically resistant to mineral oil-based lubricants and greases, many grades of hydraulic fluids, aliphatic hydrocarbons, silicone oils and greases and water to about 80 degrees Celsius. NBR is generally not resistant to aromatic and chlorinated hydrocarbons, fuels with a high aromatic content, polar solvents, glycol-based brake fluids and non-flammable hydraulic fluids. NBR also has low resistance to ozone, weathering and aging. HNBR has considerable improvement of the resistance to heat, ozone and aging, and gives it good mechanical properties. Perfluoroelastomer, polyacrylate rubber, ACM, polychloroprene, polyisoprene, polysulfide rubber, polytetrafluoroethylene, sanifluor, silicone rubber, noted for their ability to be used over a wide temperature range and for excellent resistance to ozone, weathering and aging. Compared with most other sealing elastomers, the physical properties of silicones are poor. Generally, silicone materials are physiologically harmless, so they are commonly used by the food and drug industries. Standard silicones are resistant to water, aliphatic engine and transmission oils and animal and plant oils and fats. Silicones are generally not resistant to fuels, aromatic mineral oils, steam, silicone oils and greases, acids or alkalis. Fluorosilicone elastomers are far more resistant to oils and fuels. The temperature range of applications is somewhat more restricted. Styrene butadiene rubber, thermoplastics, thermoplastic elastomer styrenics, thermoplastic polyolefin LDPE, HDPE, LLDPE, ULDPE, thermoplastic polyurethane polyether, polyester. Polyurethanes differ from classic elastomers in that they have much better mechanical properties. In particular, they have a high resistance to abrasion, wear and extrusion, a high tensile strength and excellent tear resistance. Polyurethanes are generally resistant to aging and ozone, mineral oils and greases, silicone oils and greases, non-flammable hydraulic fluids HFA and HFB, water up to 50 degrees Celsius and aliphatic hydrocarbons. Thermoplastic ether ester elastomers copolyesters, thermoplastic polyamides, melt-processable rubber, thermoplastic vulcanizate, other seals. There are variations in cross-section design other than circular. These include the O-ring with an X-shaped profile, commonly called the X-ring, Q-ring, or by the trademarked name quad ring. When squeezed upon installation, they seal with 4 contact surfaces (2 small contact surfaces on the top and bottom. This contrasts with the standard O-ring's comparatively larger single contact surfaces top and bottom. X-rings are most commonly used in reciprocating applications, where they provide reduced running and breakout friction and reduced risk of spiraling when compared to O-rings. There are also rings with a square profile, commonly called square cuts, lathe cuts, or square rings. When O-rings were selling at a premium because of the novelty, lack of efficient manufacturing processes and high labor content, square rings were introduced as an economical substitution for O-rings. The square ring is typically manufactured by molding an elastomer sleeve which is then lathe cut. This style of seal is sometimes less expensive to manufacture with certain materials and molding technologies, especially in low volumes. A physical sealing performance of square rings in static applications is superior to that of O-rings, however in dynamic applications it is inferior to that of O-rings. Square rings are usually only used in dynamic applications as energizers and cap seal assemblies. Square rings can also be more difficult to install than O-rings. Similar devices with a non-round cross-sections are called seals, packings or gaskets. See also washers. Automotive cylinder heads are typically sealed by flat gaskets faced with copper. Knife edges pressed into copper gaskets are used for high vacuum. Elastomers or soft metals that solidify in place are used as seals. Failure modes. O-ring materials may be subjected to high or low temperatures, chemical attack, vibration, abrasion, and movement. Elastomers are selected according to the situation. There are O-ring materials which can tolerate temperatures as low as -200 Celsius or as high as 250 C. At the low end, nearly all engineering materials become rigid and fail to seal. At the high end, the materials often burn or decompose. Chemical attack can degrade the material, start brittle cracks or cause it to swell. For example, NBS seals can crack when exposed to ozone gas at very low concentrations, unless protected. Swelling by contact with a low viscosity fluid causes an increase in dimensions, and also lowers the tensile strength of the rubber. Other failures can be caused by using the wrong size of ring for a specific recess, which may cause extrusion of the rubber. Elastomers are sensitive to ionizing radiation. In typical applications, O-rings are well protected from less penetrating radiation such as ultraviolet and soft X-rays, but more penetrating radiation such as neutrons may cause rapid deterioration. In such environments, soft metal seals are used. Challenger disaster. The failure of an O-ring seal was determined to be the cause of the Space Shuttle Challenger disaster on January 28, 1986. A contributing factor was cold weather prior to the launch. This was famously demonstrated on television by Caltech physics professor Richard Feynman, when he placed a small O-ring into ice-cold water, and subsequently showed its loss of pliability before an investigative committee. The material of the failed O-ring was FKM, which was specified by the shuttle motor contractor, Morton Thiekol. When an O-ring is cooled below its TG, it loses its elasticity and becomes brittle. More importantly, when an O-ring is cooled near, but not beyond, its TG, the cold O-ring, once compressed, will take longer than normal to return to its original shape. O-rings work by creating positive pressure against a surface, thereby preventing leaks. On the night before the launch, exceedingly low air temperatures were recorded. On account of this, NASA technicians performed an inspection. The ambient temperature was within launch parameters, and the launch sequence was allowed to proceed. However, the temperature of the rubber O-rings remained significantly lower than that of the surrounding air. During his investigation of the launch footage, Feynman observed a small outgassing event from the solid rocket booster at the joint between two segments in the moments immediately preceding the disaster. This was blamed on a failed O-ring seal. The escaping high-temperature gas impinged upon the external tank, and the entire vehicle was destroyed as a result. The rubber industry has gone through its share of transformation after the accident. Many O-rings now come with batch and cure date coding, as in the medicine industry, to precisely track and control distribution. For aerospace and military defense applications, O-rings are usually individually packaged and labeled with the material, cure date, and batch information. O-rings can, if needed, be recalled off the shelf. Furthermore, O-rings and other seals are routinely batch tested for quality control by the manufacturers, and often undergo QA several more times by the distributor and ultimate end users. As for the SRBs themselves, NASA and Morton Thiel redesigned them with a new joint design, which now incorporated 3 O-rings instead of 2, with the joints themselves having board heaters which can be turned on when temperatures drop below 50 degrees Fahrenheit. No O-ring issues have occurred since Challenger, and they did not play a role in the Space Shuttle Columbia disaster of 2003. Future: an O-ring is one of the simplest, yet highly critical, precision mechanical components ever developed. But, there are new advances that may take some of the burden of critical sealing away from the O-ring. There are cottage industries of elastomer consultants assisting in designing O-ringless pressure vessels. Nanotechnology rubber is one such new frontier. Presently, these advancements are increasing the importance of O-rings. Since O-rings encompass the areas of chemistry and material science, any advancement in nano-rubber will affect the O-ring industry. Already, there are elastomers filled with nanocarbon and nano-PTFE and molded into O-rings used in high-performance applications. For example, carbon nanotubes are used in electrostatic dissipative applications and nano-PTFE is used in ultra-pure semiconductor applications. The use of nano-PTFE in fluoroelastomers and perfluoroelastomers improves abrasion resistance, lowers friction, lowers permeation, and can act as clean filler. Using conductive carbon black or other fillers can exhibit the useful properties of conductive rubber, namely preventing electrical arcing, static sparks, and the overall buildup of charge within rubber that may cause it to behave like a capacitor. By dissipating these charges, these materials, which include doped carbon black and rubber with metal filling additives, reduce the risk of ignition, which can be useful for fuel lines. Standards: ISO 3601 Fluid Power Systems Euro O-rings, ISO 3601-1 2012 Inside diameters, cross-sections, tolerances and designation codes, ISO 3601-2 2008 Housing dimensions for general applications, ISO 3601-4 2008 Anti-extrusion rings, see also. References. External links: O-ring basics from C. Otto Garkens, Designing with Fluoroelastomers, Ditomatique O-ring handbook, written at an introductory level, standard, metric, Swedish, French and JIS O-ring sizes, O-ring gland design, static, axial, dynamic applications, O-rings and sealing solutions.